So thank you all very much for coming to my thesis defense. Thank you for spending your Friday afternoon with me. I really appreciate the time. Today I'm going to talk to you about a reconstruction of late Holocene hydrologic variability in coastal southwestern United States using lake sediments from Crystal Lake, California, a stormy affair. Okay, so let me just begin by giving you a general outline of my presentation so you know where we're headed. But first I'll cover the introduction. I'll move on to some background and set the scene for you. I'll cover the methodology used in the approach, the results, what those results mean in the discussion, conclusions and future work, and giving thanks to the people and organizations that helped along the way. For my introduction, I'll begin by explaining the significance, followed by our objectives and hypotheses with this research. The coastal southwestern United States is inundated with many metropolises, the largest of which is Los Angeles. With a large metropolis comes a high population. With a high population comes a high demand for fresh water. This is an area that is already filled with drought. It's drought-stricken, and finding fresh water is hard. It's actually imported to the region. So this presents us with a challenge, a low supply, high demand challenge. We have a lack of history in terms of extreme precipitation events, whether this is droughts or this is floods. And so we need to fill that gap. Let's get some records to tell us more about this through history. Though there are late Holocene records that tell us about general wetness and dryness, such as Lake Elsinore, Abbott Lake, Lower Bear Lake, they don't tell us anything about precipitation events or really droughts. And so we need to fill that gap in the terrestrial realm, because we have some studies from Santa Barbara Basin, but that's the marine realm. We don't live on the ocean, we live on land. So that's where Crystal Lake comes in. Crystal Lake sits at a high elevation east of the Pacific Ocean, and it should give us a really good record of these flood events. Keeping that in mind, these are the objectives for the research. 1, to reconstruct subdecadal scale hydrologic variability at Crystal Lake over the late Holocene. 2, to examine the frequency of large flood events as preserved in the lake sediments. 3, to compare the Crystal Lake record to existing regional records, north, south, and east, to examine the spatiotemporal dynamics of hydrologic variability. And 4, to evaluate what climatic forcing mechanisms drive hydrologic variability inferred from Crystal Lake sediments. From those objectives, we derive the following hypotheses. 1, that sediments from Crystal Lake reveal a late Holocene record of hydrologic variability, particularly flood events wherein A, the Little Ice Age, is a wet period from 100 to 500 calendar years before present, with the preservation of frequent flood events. B, the medieval climate anomaly is a dry period from 650 to 1050 calendar years before present, with fewer flood events. 2, hydrologic variability inferred for Crystal Lake is synchronous with Zaca Lake, but asynchronous with Abbott Lake. And we can evaluate this using a dipole test. 3, that late Holocene climate variability is explained by forcings related to Pacific Ocean atmosphere conditions in both the tropics and subtropics. Okay, so for some background, I'll tell you about the study site itself, what this means in terms of modern climate, and the period of which our focus is the late Holocene. Crystal Lake is located in the San Gabriel Mountains in coastal southwestern United States. It is located approximately 1,650 meters above sea level, approximately 50 kilometers east of Los Angeles, and 110 kilometers east of the Pacific Ocean. Originally, Crystal Lake's formation was ascribed to glaciation via moraine damming. However, later work shows that despite glaciers once existing in coastal southwestern United States, these glaciers existed at higher elevations and on northern-facing slopes. So, in terms of Crystal Lake, there are southern-facing slopes and lower elevations, meaning that glaciers are unlikely to have sustained to form Crystal Lake. So we ascribe formation to a different geologic process. In this case, landslides. So Wells, 1938, originally observed the Quaternary alluvium here in the West Pine Flats Basin. It has frequent layers of what we think are episodic landslides. And recently, work by Schurler et al. 2016 did some chronology on this landslide, which would have occurred between Mount Islip here and Mount Hawkins. And Schurler et al. Found that this landslide would have been approximately 3,900 years ago, which is really cool when you think about Crystal Lake, because it could hold up to 3,900 years of lake sediments. This landslide would have dammed a tributary of the San Gabriel River. And a fun fact, if you were on Catalina Island during the time of this landslide, you would have heard a sonic boom. A little bit about the lake geometry and size. Crystal Lake is a very small lake. It is 0.02 square kilometers in surface area, only 0.1 kilometers across its widest dimension, and 0.23 kilometers along its longest dimension. At the time of core acquisition in May 2014, from this area here, the deepest part of the lake had a depth of 5.5 meters. However, historical records and work from Wells 1938 have shown that the lake has exceeded 35 meters depth. Further, GIS analysis from former student Emily Silvera found the spillover point in the in the southeastern edge of the lake at an elevation of 1,704 meters above sea level, meaning that Crystal Lake could potentially hold up to 53 meters of water, not including sediment infilling, however. The lake itself is hydrologically closed, meaning it is fed solely from snowmelt, runoff precipitation, and possibly some groundwater. The only source of water loss is through evaporation or possibly some groundwater seepage. It is a very teeny tiny drainage basin, which is outlined here in the blue. So in the future of this presentation, when I refer to the drainage basin, this is what to keep in mind. I've outlined here the extent of Crystal Lake at the time of core acquisition, but this outer shaded area encapsulates what Crystal Lake's maximum depth could have been. This is a modern lake series, and I'm demonstrating to you here the drastic lake level changes. You can see just over the span of 20 years how much Crystal Lake has fluctuated. This is likely attributed to post-human settlement through use or groundwater depletion. And what's really cool is this prominent historical tree line that you see in all of these images. So this depicts how the maximum level of lake level extent, and actually on the western shore here there is a fallen tree, and this fallen tree has 160 tree rings. This gives us a minimum estimate of when Crystal Lake could have exceeded that tree level extent. Pertinent to current events, for example, everything that's happened in Santa Barbara County with the Thomas Fire, Crystal Lake is located in the Angeles National Forest. National Forest means lots of trees, which means there is a very real wildfire threat. Research from Rothenberg et al. 2010 found no fires have occurred directly within the Crystal Lake drainage basin, that small area I have outlined for you prior. However, there is evidence of at least 49 fires that have burned outside of the drainage basin since 1895. Wildfires are important because they precondition the slopes for failure. They become unstable, and the smallest of a precipitation event could generate a massive mudslide, landslide, as we saw in Santa Barbara. And I can't talk about Southern California without mentioning faults. So this image comes courtesy of Schurler et al. 2016, and Crystal Lake's approximate location is about here. And it is proximal to the San Andreas fault zone. With that in mind, there are two fault systems within the Crystal Lake area. The first is the Crystal Lake Fault, which underlies the lake basin itself. It is a normal step fault, and it is assumed to strike approximately north 45 degrees east. The second fault, however, falls outside of the drainage basin, so we don't believe it has any contribution in terms of lake geometry or sedimentation. Okay, some modern climate. The coastal southwestern United States is characterized as having a Mediterranean climate, meaning it has cool, wet winters and hot, dry summers, with any hydrologic variability only in reference to winter season precipitation. The drivers of this hydrologic variability are often summarized to ocean-atmosphere interactions. There's two I'm going to focus on here, the first of which is El Niño Southern Oscillation, or ENSO. ENSO is a 2 to 7 year quasi-periodic phenomena that is based off of tropical sea surface temperatures in the Pacific Ocean, where, to summarize, warmer sea surface temperatures in the eastern Pacific Ocean generate a low pressure ridge which shifts the East Asian jet stream further south, ultimately resulting in wetter coastal southwestern United States. And conversely, for La Nina conditions, there's colder sea surface temperatures and drier-like winters in coastal southwestern United States. The second ocean atmosphere phenomena is the Pacific Decadal Oscillation, or PDO. This is a multi-decadal, meaning spanning multiple decades, phenomena that's based off of northern Pacific Ocean sea surface temperatures as a result of air pressure changes, where warmer sea surface temperatures are indicative of a positive PDO phase, meaning that the jet stream is then pushed further south, likely resulting in wetter coastal southwestern United States, and conversely for a negative PDO, where we would have cooler sea surface temperatures in the North Pacific and resulting in drier summer-like conditions in coastal southwestern United States. This figure here from WISE 2010 summarizes this beautifully. So if we look up here in this top right corner, a negative SOI is the index which we use to classify, so negative SOI in this case is El Nino conditions. So we have El Nino conditions and a positive PDO. And you can see generally it is wetter in the coastal southwestern United States for the winter months. This is a standardized figure from October to March. And conversely, if we have a negative PDO and a positive SOI, we have drier-like conditions. Though we don't need El Nino and positive PDO to be in phase for wetter winters in coastal southwestern United States, it is the most notable in terms of producing those conditions. Variability in PDO alone could generate wetter conditions in coastal southwestern United States. The second feature I want to mention is the hydroclimatic dipole. The hydroclimatic dipole is, if you think of an atmospheric seesaw with one end in the north and one end in the south, and it pivots along its fulcrum approximately 40 degrees north to 42 degrees north. That area of the fulcrum is the transition zone. It means it can migrate north, south, and it's a little more ambiguous in terms of relative wetness and dryness. With that dipole in mind, one end would be relatively wetter and one end would be relatively drier. So if we were to say, look at this figure here, imagining in the western United States, we have this dipole. We've got a drier-like condition in the Pacific Northwest versus a wetter-like condition here in the coastal Southwest. The last feature I want to discuss in terms of modern climate are atmospheric rivers. Atmospheric rivers are long filamentary features in the atmosphere that transport warm, moist air from the tropics to the mid-latitudes. In fact, more than 90% of the moisture that is transferred to the mid-latitudes is because of atmospheric rivers. This is a really cool figure from NOAA, and this actually depicts an atmospheric river that had been in the Pacific Ocean about 2 weeks ago. And you can see the warm, moist air coming up from the tropics as it approaches in that filamentary feature into where it's about to make landfall in Northern California, Southern Oregon. When an atmospheric river makes landfall, it dumps a great amount of precipitation, and even more so with orographic lift. With orographic uplift, it dumps a lot more precipitation and very likely floods. Most of California's notable floods are due to atmospheric rivers. The paleoclimate setting in which I'm going to focus on for this presentation is the late Holocene. In the late Holocene, there are two primary features to focus on. The first is the Little Ice Age. The Little Ice Age can be summarized as a period from 100 to 500 calendar years before present. It is one of the most wet and cold periods during the late Holocene. And keeping that in mind, the strength, duration, and timing is variable, meaning one record could record peak wet conditions from 150 to 350 calendar years before present, where another record may record peak wet conditions from 350 to, say, 500 calendar years before present. The second feature is the medieval climate anomaly. And again, to summarize, this is a period from 650 to 1050 calendar years before present. It's typically regarded as a warm and dry period, but with intermittent wet intervals. And again, it is variable in strength, duration, and timing. So into the methodology. This is the methods we use, and I'm going to just take you right through it. Let's begin with core collection in May 2014. This is the raft we used to collect 2 sediment cores from the deepest part of the lake. We collected 2 cores for lateral continuity and performed the same basic sedimentological analyses. However, in this study, I focus on the longer, more complete core, which is CLPC 14-1. Post-collection, the cores were split. This is a picture of me actually cleaning the cores for core descriptions, where I note any changes in sediment color, sediment textures, and the presence or absence of any sedimentary structures. After descriptions, the cores were photographed and then sampled for analyses. So for the most recent 200 years of chronology, this comes courtesy of Rothenberg et al. 2010's lead-210 and cesium-137 dates. For the radiocarbon dates, this is the only picture I have. I was too scared to take pictures in the University of California, Irvine, but I actually got to bring our samples, which were woody material or charcoal, and prepare them and run them at UCI's Keck Carbon Cycle AMS facility under the supervision of Dr. John Southen. After analyses, all radiocarbon dates were calibrated to calendar years before present. For physical analyses, we ran magnetic susceptibility at 1 centimeter contiguous intervals, rotating the sample once on the vertical axis 180 degrees. The second physical analysis was for loss on ignition, or percent total organic matter at 550 degrees Celsius and percent total carbonate at 950 degrees Celsius. This was also at 1 centimeter contiguous intervals. Just a side note for percent total total carbonate, any values that were 4% or less we regard to as 0% because it's more likely the result of clay dewatering than carbonate loss. The last of the physical analyses we ran was for grain size. All of the grain size samples at 1 centimeter contiguous intervals were pre-treated to remove organic matter, carbonates, and then biogenic silica or diatoms. They were run in classifications for percent clay, percent silt, and percent sand. For the first chemical analysis, this was run externally at the University of Saskatchewan Isotope Laboratory under the supervision of Dr. Bill Patterson, and this was at every other centimeter. For example, 0 to 1 centimeters, 2 to 3 centimeters, and we sampled for organic carbon to total nitrogen ratios, converting to molar values post-analysis. The second chemical analysis was on acidified samples similar to those of the CN ratios, and these were conducted in Dr. Sean Lloyd's laboratory, also sampled every other centimeter. The last analysis we ran was for seismic reflection profiles in multiple transects across Crystal Lake. However, post-analysis, courtesy of Dr. Joshua West at USC, we reveal we only covered the sediment-water interface, and therefore these data are not referred to elsewhere in the study. All right, what does this mean? So let's go through the results and we'll see. So as we were going through our core descriptions, we noticed two distinctly visible different types of sediment. And over the next few slides, I'm going to point this out to you, and then later I'll tell you about the significance. So I've got my strat column here where sediment color reflects the sediment color in the core, and any textures or sedimentary structures are represented in the explanation. This is a summary of the radiometric ages. These four that are highlighted in red are not used in the age model, and I'll discuss this in a little bit. You'll see over the next few slides that I have some gray units that are highlighted and not gray units. Keep this in mind. I'll show you a table at the end of my results which summarizes the gray versus the not gray, but they are important. So here are the magnetic susceptibility values, the percent total organic matter values, percent total carbonate. It's very hard to see, but I promise you it's there. There is a very thin yellow line for that 4%. It looks better on paper. And percent grain size in each of the classifications for percent clay, percent silt, and percent sand. Organic carbon to total nitrogen ratios. I'll explain this in the discussion. And then for the bulk organic carbon isotopes, this is all of my data. And now to summarize it in terms of a table. Those gray units I pointed out, these are these black values here, and the non-gray units are summarized in the blue. You can see here that there is a difference between the black and the blue values in both averages, but they are all statistically significant. So what does this mean? It means that there's two basic types of sediment, and I will cover that for you now. So in my discussion, I'm going to cover that lake sedimentation. I'm also going to take you through the age model and how it was derived, and then what this all means in terms of paleoclimate implications. For lake sedimentation, we have two modes of sediment. The first is ambient sedimentation. Ambient sedimentation is characterized as normal lake conditions, where we have autochthonous organic sedimentation, autochthonous chemical sedimentation, and allochthonous sedimentation, including both aeolian and runoff generated sedimentation. The second mode of sedimentation is event sedimentation, and we classify this as geologically instantaneous. And this could be flooding, earthquake disturbance, or fire-related runoff sedimentation. So now I'm going to bring you through both ambient and event sedimentation and how we classify them in terms of physical and chemical properties. The thing I'm going to show you is this ternary diagram, and this classifies the grain size. And for an ambient sedimentation process, we would expect a lower energy environment. And with a lower energy environment, we typically see finer grain size. Well, our average grain size is a sandy silt with a good clay contribution. And this is what we would expect for a lower energy environment. Further, when we look at our strat column, we see possible laminations. And these laminae are diagnostic features of deep water conditions, lower energy conditions, where there's a deep lake and there's bottom water anoxia, which inhibits bioturbation. For chemical properties, this is a classic figure from Myers and Lallier-Verges 1999, and it really summarizes both primary productivity and organic matter source, where organic carbon to total nitrogen ratios summarize the organic matter source, and in this case for our study, primary productivity explained by isotopes. So I'll pull up a table for you, and here is our average CN ratio for our ambient data, where you can also see, if you look at these blue dots, they tend to cluster along that algae mixed border. Algae is typically CN values of 4 to 10, and terrestrial is typically 18 plus. Anything in between that we say is mixed, meaning it has contributions from both algae and terrestrial. For ambient sedimentation, we would expect more in situ sedimentation coming from algae. Further, when we look at our isotopes, we see we have a lower value, and this lower value is more diagnostic of increased primary productivity, meaning phytoplankton are having a great time taking up the lower energy carbon-12. Event sedimentation. I want to start event sedimentation by just giving you a blanket statement and saying that our sampling was at its highest resolution of 1 centimeter, which means that if we found what we thought were event sediment packages, they had to be 1 centimeter or greater in thickness in order to be statistically robust enough. And so this is just a minimum criteria. This means there could have been more RDLs in the record, but we just simply did not sample at a high enough resolution to consider it statistically robust enough. I will also use through the next slides events, flood events, RDLs interchangeably, where RDLs stand for rapidly deposited layers. Okay, so again, I'm going to pull up this ternary diagram for you, but this time we're going to look at all of these black squares. And we see in our summary table that our event sediments are now silty sands with a lower clay contribution. And this is what we would expect for a geologically instantaneous event where there's a higher energy environment which can transport more coarser grains into the lake. And if I pull up the strat column now, our event sediment packages are typically like a, let me find the mouse for you. I want to zoom in. They're typically characterized by a often sharp basal contact, which has coarser sediments, and it also has visible organic matter. And then you transition to a dark to medium mud with less coarse material, and finally it is capped by beautiful mud. Here's another beautiful one right here. I mean, it's the thing we dream of in terms of mud. It's cohesive and light brown. Okay. And I wanted to pull aside a few of these close-ups of some of the event layers. And you can actually see with the sand, and this is the most beautiful and clear to see, this sharp increase in percent sand, and then a gradual decrease as you move up core. And we see this over and over again down core. Okay, so for chemical properties, I'm going to pull up that same plot, that same cross plot, but this time we'll focus on the black squares. And you can see how they kind of cluster here more along that terrestrial and that mixed terrestrial border with an average of 19, which is definitely in that terrestrial realm. Also, we have our organic carbon isotopes that have higher ratios. And we expect this of terrestrial organic matter. There's two primary types of organic matter. There's C3 and C4 plants. And terrestrial organic matter is typical of these isotope values and of these CN ratios. So let's pull up this table again. Here's that table, but now in terms of event and ambient sedimentation, where event is the black bars and ambient is the blue. Again, you can see we have differences in our averages, and they are all statistically significant. They are all different. And to bring up the composite figure, I alluded to the gray units being important. Well, the gray units are these event layers. And so here you can see them versus depth as events 1 all the way through events 14. I showed you that close-up in my strat column. Well, this is that same event. And you can see down here we transition from that dark brown with the organic matters all the way up to that most beautiful mud up here. And so this is really a picture of what we would see down core. This is a model which summarizes what we believe is happening in Crystal Lake to generate these RDLs, and that these are the result of large precipitation events that rapidly mobilize high sediment loads from the drainage basin, pulling up sediments and terrestrial organic matter, similar to that of a turbidity current. So we have a high sediment load during a flood. It makes its way to the lake, scours, and then flows as a turbidity current, leaving us with the typical graded sort of bedding where we go coarse to fine associated with turbidity currents. Keeping this in mind that these are instantaneous events, this really changes and develops how we approach our age model. So here's our ages again, and these 4 red ones, 2 of which were in sediments that were reworked, and 2 of which were sampled in event layers. When we were sampling for radiocarbon dates, we want to sample in ambient sedimentation versus something that was being washed in from the watershed. To see how we approached our age model, we've followed other protocols such as Brown et al. 2010. And to do this, we took all of the RDL packages and we condensed them to 1 centimeter to normalize them as these instantaneous events. So regardless of the original event thickness, for example, event 1's original thickness was 79 to 88 centimeters, and we condensed it to 79 to 80 centimeters depth. And we did this for all of them. Then we used the equation of a line to generate the slope between each of our age points. And that was used to determine the down core ages. Where we reached RDLs, RDLs are confined by a minimum and a maximum, yet we plot them versus mean. I'll show you that in a moment. So this is our original age model. And after we condense all of those RDLs to instantaneous moments, we are left with this age model. So here is the figure that summarizes the work from Crystal Lake, where we have our events plotted on their mean age and error bars between the minimum and maximum ages. They are plotted versus event thickness. And just to highlight this, since I've already highlighted it for you, the gray box here encompasses the 3 largest of these event layers in terms of thickness. However, they are stacked intervals, which means they are just one on top of the other. And the only chronology we can truly provide is the minimum and maximum ages. So 3 events, the 3 largest events, occurred within approximately 100 years of one another. They could have been the same event, one after the other, or it could have been 20 years between them. We don't know. Yet we do explore alternative hypotheses other than large precipitation events. The first is that these are mass wasting events associated with earthquakes. We are close to the San Andreas, so we explore this hypothesis by comparing our event record to paleo earthquakes from Weldon et al. 2004 study in Wrightwood, California, along the San Andreas Fault. In comparison to, we're going to look at these gray triangles and their associated error bars. In comparison between my record and Weldon et al. 2004's, we see that event 2, event 6, and event 13 are the most likely, given that those corresponding paleo earthquakes would have had 3 meters of offset or more. However, the error associated with these paleo earthquakes is so large it's actually inconclusive. For example, looking at event 13 here, the error bars associated with that paleo earthquake encompass almost event 13 and event 14. So we disregard these paleo earthquakes in terms of the more favorable and conservative approach that these are precipitation events versus earthquake disturbance events. The second hypothesis we explore is that these are post-fire substrate preconditioning events. Now, I've already mentioned that there is no record of fires burning directly within the Crystal Lake Basin, and any fires outside of the drainage basin do not matter in terms of post-fire substrate preconditioning. Further, Biswell 1974 shows the frequency of approximately 25 to 30 years for any fires in the San Gabriel Mountains. And because Crystal Lake's drainage basin is so small, that's more than likely a much lower frequency than that from Biswell. So we also disregard this hypothesis in terms of the more favorable, but charcoal counts would really give us some more information on that. So keeping in mind that the RDLs represent large flood-producing precipitation events, these are our paleoclimatic implications. The first is that we have 1,300 years of stormy affairs, where more RDLs occurred during the medieval climate anomaly than during the Little Ice Age. However, when we look at our event thickness, we actually see that events during the Little Ice Age are thicker than those during the medieval climate anomaly. And though we can't quantify on an absolute scale, we do believe that there is some relative relationship between event thickness and either storm duration or storm intensity, meaning that the largest storms were likely during the Little Ice Age. Our second implication is that RDLs tend to cluster. We see 3 clusters of 2 or more RDLs. And this suggests that there are long periods of time in which either large storms are infrequent or that the drainage basin is less susceptible to large precipitation runoff. Regional comparisons. Though our record is a study of large precipitation events, and the only real regional comparisons we have are to regional wetness and dryness, it's important to compare because maybe we can make sense of if there's any relationship between general wetness and dryness and these precipitation events. So here are the records we compare. From the terrestrial realm, we compare to Abbott Lake from Heiner et al. 2016, from Zaca Lake, Kirby et al. 2014, from Lower Bear Lake, Kirby et al. 2012, and from Lake Elsinore, Kirby et al. 2010. From the marine realm, we compare to Santa Barbara Basin flood events from Hendy et al. 2013, from Santa Barbara Basin pollen from Huser et al. 2015, and from Coastal California sourced Mojave Lakes from Miller et al. 2010. So when we refer to this, we regard increases in percent sand, increases in mesic vegetation, and increases in molar CN ratios as wetter than average climates. So let's look at it in terms of our clusters. The first is in cluster 1, we see wetter than average climate states in all records except for Abbott Lake, which suggests that there are latitudinal differences between coastal southwestern United States climate regimes. The second cluster reveals less than apparent wet to dry relations. However, we see that right here, where Crystal Lake storm events and mesic vegetation onset begin, are darn near synchronous. And we also see here that there is Mojave lakes, which goes to show us that regardless of wetter than average or drier than average conditions, we see that we have RDLs in the medieval climate anomaly. So a typically drier period, and we have a wetter interval. In terms of the third cluster, we see, again, latitudinal differences where most every other record, except for Abbott Lake, shows drier than average conditions. And what this means in terms of synopsis is that although background climate states matter, we see these RDLs regardless of general wetness or dryness. To summarize in terms of the Santa Barbara Basin flood events, there is the possibility that events 1, 4, 5, and 6 coincide with some of the Santa Barbara Basin flood events. However, Santa Barbara Basin is a much larger catchment. So to generate a flood or flood events in Santa Barbara Basin, you'd need a much bigger or much more prolonged precipitation event versus the small drainage basin of Crystal Lake. So that may explain why we see more of these precipitation events, these RDLs, in Crystal Lake as opposed to Santa Barbara Basin. Now, can we make sense of any of these flood events in terms of ocean atmosphere mechanisms? So to do that, we evaluate reconstructions from the Pacific Ocean-based studies. The first of which is a PDO index reconstruction from McDonald and Case, 2005. The second is a North Pacific PDO sea surface temperature reconstruction from Mann et al. 2009. The third of which is a Santa Barbara Basin sea surface temperature record from Kennett et al. 2007. And last, a tropical Pacific sea surface temperature gradient reconstruction from Rustic et al. 2015. And what did we see? We actually observed no consistent or persistent relationships between the Crystal Lake RDLs and Pacific Ocean reconstructions. Why do we think this is? The first is that Crystal Lake is such a small drainage basin, it provides such a narrow target for the jet stream, for this storm track, that it's very possible that the storms just simply missed Crystal Lake. The other explanation we suggest is that the temporal scales are vastly different in terms of the reconstructions are either on decadal or interannual temporal scales, and these are instantaneous events. And so it's less likely that we are going to recover an instantaneous event during decadal or interannual reconstructions. So to summarize and tell you what I would do next. We have a new 1,300-year subdecadally resolved terrestrial sediment record from Crystal Lake. It is a record of late Holocene extreme hydrologic events. And although we explore alternative hypotheses, we find that RDLs are most likely the result of storm-induced events. In terms of regional comparisons, we find that RDLs occur during both wet and dry climate states. And there's also some indication of latitudinal variability in winter precipitation, and this also suggests possibly that the hydroclimatic dipole does extend longer than 500 years. But we see no apparent relationship between RDLs and Pacific Ocean driving mechanisms. And regardless, large flood-producing storm events have occurred in the late Holocene and will occur in the future, no matter if it's wet or dry. So to bring it on home, I'm going to go through my hypotheses again for you. And what did we find? We actually found that the Little Ice Age was a wet period, from 100 to 500 calendar years before present. However, with the preservation of fewer but larger magnitude flood events, that the medieval climate anomaly was a dry period from 650 to 1050 calendar years before present, with the preservation of frequent but lesser magnitude flood events. That latitudinal variability in winter precipitation exists. For example, what we see in event clusters 1 and in 3. And finally, that there is no apparent relationship between RDLs and Pacific Ocean driving mechanisms. So what would I do next? I would do bigger, meaner coring. I'd go in with a proper drill rig and drill down to get more sediment, more mud. We know that Crystal Lake could hold up to 39 years of sediments, so why not go in and get more mud? And the next thing I would do, and these are actually former student Robert Leeper's hands sampling for it, is volumetric charcoal analysis.
Yours.
No, they're not mine. Nope. But this would actually provide some context into whether or not fires play a role in these RDLs. Do they actually precondition the slopes? And improve the age model. Really button it up, and Amanda had this really corny joke for me to say to you all because it's being run with bacon and everything's better with bacon. And to set better traps because we didn't capture Bigfoot, and so we really got to go back. I mean, it's a standard in the Kirby lab. So with that, I just have my thanks to give, and then I'll take questions. All right. So I just want to thank the man, the myth, the legend, Dr. Matthew E. Kirby, for what? I had to, for sticking by me for so many years and not entirely giving up on me when I gave up on myself sometimes. So thank you. For Dr. Nicole Benuso and Dr. Sean Lloyd, I didn't have a picture with you, Sean. I'm sorry. I guess we're going to have to take a selfie after. But thank you for being on my committee. Thank you for letting me use your lab. Thank you for being an all-around badass. So, for some of the organizations and the people, Dr. John Southen at UCI, Bill Patterson at University of Saskatchewan, Dr. Josh West at USC, and from my funding sources, ASI, the Los Angeles Basin Geological Society, Sigma Xi, and NSM ICC for letting me go and present this at multiple conferences. And for the people who helped not only in the lab but in the field, Christine, Megan, Leeper, Tracy, Jeremy, Emily, Stash, and NASA, who did some awesome micro-fossil counts. For the wonderful people who helped me in having a great experience during this time, some friends and some great memories. And for the most important people in my life and cats, for Christine and Amanda, thank you both. I mean, I couldn't pick one or the other. You guys are the best. Thank you. The cats are just awesome, and they're therapy. So you need it during these tough times. And for my family, both near and far. So thank you all for standing by me. And with that, I will take questions.